Okay, so we're going to talk about oblique triangles and the law of sines. And okay, so we're going to discuss triangles that are not right triangles. Wow. And we can't really discuss the law of sines without reviewing congruence and oblique triangles. So that's actually where we're going to start. So when are two triangles congruent? So they're congruent when their corresponding sides and angles are equal. So you might remember these from the days of geometry, the congruence axioms. So we had like side, angle, side. So this is when two sides and the included angle of one triangle are equal, and two sides and the included angle are equal to two sides and the included angle of a second triangle. So side, angle, side. So notice how I've got one mark here. So I marked them and I color coded them just so that you could see. Here would be how we'd represent two congruent triangles that have the side, angle, side axiom to go along with them. And the included angle means the angle in between the two sides, okay? All right. So next we have angle, side, angle. So that's when two angles and the included side of one triangle are equal to two angles and the included side of a second triangle. So angle, side, angle, angle, side, angle. Works like that, okay? All right. And then we also have side, side, side. So that's when three sides of a triangle are equal to three sides of a second triangle, respectively. So we look something like this. And so just to kind of give you a crash course review of congruence, so does side, angle, angle ever hold? Okay, so do we have that type of congruence axiom? So if a side and any two angles are given, you can, sorry, I just realized I made a spelling or a hand typo there. So you can determine the sum of the angles to determine if angle, side, angle holds. So we technically don't have side, angle, angle, but what you can do is you can manipulate this to see if you have angle, side, angle. So let me show you what I mean, just a quick review of this. So I've got this triangle here, so I've got the side 14, and then I've got, so this angle here is 20, and this angle here is 50. So I want you to notice how this is set up. I have two other triangles. So notice with this triangle, the 14 falls in between the 20-degree angle and the 110-degree angle, versus this triangle, I have 20, 110, and then 14. So you can see that they're different, right? They're not the same. So the way that we would use this would be the side, angle, angle. I'm going to manipulate this. So I take 180 degrees because I know that the angles, the three angles in a triangle need to add up to 180. So I take 180 minus the 20 minus the 50, and I get 110. So now what I find here when I think about which one of these two is congruent, so notice I have this angle, this side, and then this angle. So this triangle now is actually different. This would not be congruent because I have 20, 10, and then the side. But here I have 110, 14, and 20, 110, 14, and 20. So this would hold by the angle, side, angle axiom. Okay, so how do we figure out the other sides or angles of a triangle if it's not a triangle? So where is this all going? Well, to do that, we must know at least one side and any two other measures to solve a triangle. And there are really four cases for solving oblique triangles. So when you have a right triangle, you can just, use your sine, cosine, tangent to figure out the sides of the triangle. It's pretty easy. When you have oblique triangles, we break this down into four separate cases. So the first case, we know one side and two angles. So side, angle, angle, or angle, side, angle. That's the type of congruence that holds. Case two would be that we know two sides and one angle that is not included in between. So that would be side, side, angle. So this could make actually more than one triangle, and we will discuss why this is complicated in another video. Case three is that two sides and the angle are included, or are known. And then the fourth case would be that we know all three sides. Okay, So those are all the different congruence axioms and how, like, in those cases, we can figure out what's going on with the triangle and we can solve all the sides and all the angles. Now, what about if I had angle, angle, angle congruency? Could I figure out the different sides of the triangle? You can't. And by the way, angle, 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 this is not guaranteed to be congruent. You just have similar triangles, but they're not congruent. They're not going to end up being like equivalent triangles. Okay, so anyways, so back to those cases. So case 1 and case 2, if you have those types of congruency, we're going to use what's known as the law of sines, and that's what this video is about. For case 3 and case 4, we're going to use the law of cosines. That's a different video. But basically, like when those conditions hold, we can figure out the different sides of an oblique triangle. So now we're going to talk about what the law of sines is, and I'm going to just explain to you how, like, where does this come from. So just a quick little proof. So we're going to start with an oblique triangle, and it could be either acute or it can be obtuse, whatever. And so the thing about either one of these is to figure out the height of the triangle, we can kind of use these little pink sketches that you see here. We can use this as an aid to help us figure out the triangles. But by creating these little side sketches, I want you to notice what happens. I end up getting right triangles. I get a right triangle here, I get a right triangle here, and then in this case I have a right triangle now from here to here. So by adding on these little sketches, we can now leverage what we know about right triangles, because I've effectively made a right triangle out of both of these situations, right? So I can notice if I wanted to say find sine of A or sine of C, in either case, this is going to hold. So let me just make this clear. So the sine of A and sine of C, these equations I have, they hold for both triangles. So for sine of A, so if I want to find sine of this angle, it's going to be the opposite over the hypotenuse, right? So opposite over hypotenuse, same thing here. If I want to find sine of A, so look at the little right triangle that gets made here. So this is going to be h over c. So in both cases, sine of A is h over c in both of these. What about sine of C? So for sine of C, so here's C, so this is going to be h over A in the first triangle, and then sine of C in the obtuse case, this is also going to be h over A. So these relationships hold whether you have an acute triangle or an obtuse triangle. So I have these two relationships, and in both cases, h is the same height, right? So these situations hold in both triangles. H is the same in both pictures. And so I can manipulate these equations and I can solve for h. So if I solve for h in both equations, I get that h is c times sine of A, or h is A times sine of C, just rearranging. And now that I've solved for h, I can actually set this equation and this equation equal to one another. So see, like this. And now here is the cute thing. Now, if I divide both sides by sine of A and divide both sides by sine of C, I get this relationship here. A over sine of A equals C over sine of C. And this is what's interesting. This shows us a relationship now between the angles and the sides of our triangle. And using similar logic, we can also show that B over sine of B equals C over sine of C, A over sine of A equals B over sine of B. So we can, I'm going to skip over that, but same logic. And so this actually creates what's known as the law of sines. So in any triangle ABC, and sines little a, little b, little c, we have this relationship. This is the law of sines. Or, in other words, the lengths of the sides in a triangle are proportional to the sines of the measures of the angles opposite of them. So that is what the law of sines says, and this allows us then to solve different triangles, and I'm going to show you how to do that in a second. But the last thing that I just want to mention to you, there's an alternative form of the law of sines. You could have the sine come on top and then the sides come on bottom. So they're equivalent, and it's just an alternative form. Okay, so as far as actually using the law of sines, I think it's pretty straightforward. So I've got, I want to solve triangle ABC if A is equal to 28.5 degrees, C is equal to 102.5 degrees, and little c is equal to 25.1 inches. So here's my situation. And now I'm going to show you how to use the law of sines with this. So I can use the fact that A over sine of A should be equal to C over sine of C. And I just used basically part of this equality to help me work through the problem. So coming back to this, so if A over sine of A equals C over sine of C. So I know sine of A, I know sine of C, I know little c. So I can plug all those in as you see here. And so now this is a pretty simple algebra problem, right? Because now I'm just going to solve for A. So I basically just multiplied this sine of 28.5 to the other side, and then I can figure out what A is. So I can go through and solve that. And now I have figured out what the length of this side is. Okay, so let's keep going. So what about, now I have to figure out angle B and then side B. Okay, well, figuring out angle B is pretty easy, right? I can just take 180 minus the other two angle measures, no problem. And if I do that, I get that this is 49 degrees. So then I've got that this angle here is 49 degrees. I don't know this, but I can leverage the other information in this problem. So I could now take the side C over sine of the angle C. So I set up basically that same proportion. Now I can solve this. So I get, I can just multiply sine of 49 degrees to both sides. So I get this equality here. And so ultimately I'll get that B is equal to 39.4 inches. So this side is 39.4 and this is 49 degrees. And so check it out. I have solved all the different sides of this triangle. Okay, so that's how you can use the law of sines. Another surprising application of this has to do with the area of a triangle. So normally we would think of the area of a triangle as 1/2 b times h, but this can be tricky if we don't know h. So what we can do then is we can think about this situation here where I either had a obtuse triangle or an acute triangle, and we can think about how we drew a sketch to help us kind of figure out where h is or how to get to h. And we can think about those relationships with sine and h and the other sides. So for instance, if I wanted to find sine of A, that would just be h over c in either case, right? So even here, sine of A, that's h over c. So what that means then is this h, which is hard to find, I can actually solve this equation, solve it for h, and get this as c times sine A. And so now in doing this, so notice that the base in both cases is this side B. I can now replace this h with this c sine A. So A can alternatively equal 1/2 BC sine A. And if you were to switch the different sides, so if you were to change, you know, which side we're talking about, there's other equivalent ways to write this. So if you have the side angle side kind of congruence, or you know that information, these are the three different formulas that you can use for the area of a triangle. So you actually don't need to know the height. So this releases you from having to know the height. Now, as far as like remembering all of this, you actually don't have to perfectly remember these formulas. I'm going to show you how to use them. The big thing is that you have this side angle side situation here, that you know that piece of information. So first, let's just use the formula, and I'll show you kind of how to optimize it. So I want to find the area of this triangle. So notice I know this side, this angle, and this side. So I've got side, angle, side. And this angle is B. So when I think about like what form of the formula would I want to use, it would be this right here. But I want to point something out. So notice this side here, this side would be little c because it's the one that's directly across from angle C. And this side here, this side would be little a because it's the one that's directly across from angle A. So notice that actually in how this formula was, like how we made this formula, B is that angle that falls in between the two sides. That's actually what these formulas are getting at. Whatever your angle is, it should fall in between the two sides. So you multiply the two sides that you know times the angle, sine of the angle in between. That's the shortcut formula. Okay, so now I can just plug this information in. So I've got 7, 13, and sine of 120 degrees. And I can multiply that all together to get 39.4 feet squared. Okay, so let me just walk you through that one more time. And I made just a slight change to the problem to make this nicer on us. Okay, so I now want to find the area of this random triangle DEF, and I'm given this information. So you actually know how to set this up in that, so I have this triangle DEF. So you label the three sides. So the side little e, that's going to be directly across from angle E. So that goes here. So notice what happens here then. Just by how you set up the triangle, you end up with the angle, the side, and the angle. So I want to find the area of this. And remember, what we need to use this formula is we need to know the side angle and the side. So you'll notice, right, I'm lacking some information. I have the angle, the side, and the angle. So to use the formulas, we need the side angle and the side, so we need to figure out another side. So now I'm going to use the law of sines again to help me figure this out. So I can pretty easily figure out angle E. How can I do that? You should try to figure that out on your own. So angle E I can figure out by just taking 180 minus the other two angles. So I get E is equal to 48 degrees and 20 minutes. Okay, so if you want to follow along with me, I want you to find side F, side little f. That's what I'm going to do. So I recommend that you pause the video and just try to use the law of sines now to figure it out, and then hit play when you're ready. Okay, so I've got side E 31.2, and then we figured out this angle measure. So this is sine of 48 degrees and 20 minutes. I don't know this side. I need to figure this out. And then I've got the angle measure F here, so 73 degrees and 30 minutes. So I can go through and I can figure out what F is. So I've omitted the calculations here, but it comes out to 40.0. I rounded to 40.0. Okay, so I've marked this side, and now notice what I have. I have a side, an angle, and a side. That's the information that I need. So when I set this up, notice how I've set this up. I have this side, and then sine of the angle in between. So that's why I say you don't have to memorize that formula. You just need to make sure you have the side, the angle, and the side, and then it pops out pretty nicely. The key to remember with this is that you get that angle in between, okay? So then I can just complete this calculation, and then there you go. So now we've used the law of sines and we've applied it to a special case with area. So I think that kind of covers this topic. So I will leave it at that. And thanks for watching, guys. I'll catch you in another video.